Hi everyone, I'm Eneko Lazpita, a PhD student on the Model Flows group, and today's video is going to be part of a video series we are making on our group Model Flows, which will be about how to set up a CFD simulation of a left ventricle model. In today's case, more particularly, we're going to talk about how to preprocess the geometry of left ventricle and how to obtain the wall movement of the ventricle. So, as I just said, the tutorial is going to be about the preprocessing of the geometry. And first, just mention the different softwares we may use or have to be able to access to do this tutorial. First would be the MATLAB, since our scripts of the STL generation are written in MATLAB. Then some open source software we're going to use for the segmentation and the preparation of the patient-specific geometry, which we are going to introduce later, which is 3D Slicer, MeshLab, and ParaView. And then for the data we need to create the data. You need to create the data using a CAD creation software, whichever, to create this idealized STL file. While for the medical data, you should have some CT cardiomyopathy scans. So the general overview of the method of doing these left ventricular simulations is the one that you see here. So we can have some idealized geometries, such as the one you see here, which are geometrically more simple, and we can construct it using some CAD software. While on the other hand, we also may have some more patient-specific, more realistic geometries, which we need to segment and prepare for the following meshing and simulation, etc. And in both cases, if you have the evolution of the STL files or of the geometry, you can directly go to the meshing and then do the simulations. But the potential of the tutorial today is to show you our scripts in MATLAB to generate these STL files. But apart from that, we also want to introduce you to the segmentation and how to obtain a clean left ventricle from medical data. But well, first we're going to center on a more easy geometry, which would be an idealized left ventricle, which in our case, this geometry we have extracted it from Zeng et al. 2012, and as you can see here, the geometrical features are quite simple. In the end, the ventricle is a semi-ellipsoid, and here you have all the parameters needed for the generation of this geometry. So once we use a CAD software or some tools to generate this geometry, we are going to go to our STL file generator in MATLAB, and what this file or this script is based on is in obtaining the volume variation of the left ventricle by integrating the flow rate data. For this, we also have to first classify the points of the left ventricle, which in our case the inlet and outlet tubes are going to be static, and the shell and some region on the base plane of the left ventricle will be moving. As you can see in yellow, we move the points, and in blue we are going to maintain them static. So as I said, then the movement is going to be extracted from the flow rate data via integration. And in our case, as we know how the semi-ellipsoid volume is, we can also we will going to use this equation and also the relation between the short and long semi-axes to know how this geometrical feature, semi-ellipsoid, will be in each time step to obtain this, to match this volume variation. And for that, we're going to use a MATLAB script, which before going to MATLAB and run it and see it step by step, we're going to see here some general pseudocode, which, well, we start by loading the geometry, of course, and doing some scaling and classification of the points and their connectivity, which is really important because we need to maintain the connectivity of each point between the STL files for then in the simulation to have this correlation. Then, as I mentioned in the figure earlier, we have to classify the vertices which are moving and which are static. Then, before generating the STL files, we need to process the flow rate data, and by of course reading it, doing some interpolation and matching the diastole and systole wall movement in the end, and then we're going to calculate the volume variation via integration. And here, another also important thing is to define the time steps we want to create, because it will be the same time steps for our STL generation. And finally, we will generate our STL files, which for each time step, we're going to calculate the scaling factors for each ventricle dimension, then apply the displacements both for the shell and for all the moving points in the shell and also in the base plane, and write the STL files. And finally, we also have a part of the code which is to prepare the inlet and outlet data, which is basically taking the flow rate data that we have and create some inlet velocity or outlet flow rate, which is going to match the volume variation in our ventricle. So with this, we are going to go to the MATLAB script that we have. And here, we're going to run each section to see what we're doing in each part of the code. And well, of course, we're going to reset our whole workbench. And as I mentioned earlier, we're going to load the STL file. Then we're going to apply some scaling. In our case, the code is in meters. So we're going to convert, and the data is in millimeters. So we're going to convert this data to meters. And also, as I mentioned here, we're going to extract the points and the connectivity of each point. So if we run here, we're going to see that we have loaded the STL file, our mesh. There you have it. And then, now again, we mentioned that we want to classify the different points that are moving and not moving. For that, we first need to introduce a tolerance, which is how we catch, in the end, even if you have points in zeta 0 plane, there may be some discrepancies because of the computation error of the machine. So we introduce a tolerance, and also we define the short semi-axis here to classify the points together with R-move, which is the radius which in the points will start to move in the base plane after the tubes. So with all this, we can define the points that are at the base plane, the ones that are below the base plane, and the ones that are up on the base plane, and classify the data between moving and static points. So with this, we get the following picture, which, again, in yellow we have the moving points, and in blue we will have the static points. And well, once we have this classification done, as I said, we want to include the flow rate data for the afterwards integration to obtain the volume variation. But in this section, if we run it, we will first, of course, load our flow rate chart which we have in a file. Here you can also define which is your period. In our case, it's 1, and also the integration points, because we want to have a smooth graph for the afterwards integration. So here we are going to do some interpolation, which is here, and also some correction, as I said, of between to correct the differences that may be between the diastole and the systole, which we finally have to we need to have the same volume variation in both of them. And if we run this, we will get the picture of the flow rate data and the interpolated flow rate data. As you can see, in our case, we already had some fine chart, but if you have another graph that you want to introduce for the flow rate data, you may have to adjust the code a little bit to have this smooth graph. And well, finally, well, not finally, but now we also, as I mentioned, we need to define the number of STL files we're going to create, which is the points of integration we will have in the volume variation. Also, we need to define the initial volume of the ventricle in milliliters, because as our flow rate data was in milliliters per second, here the volume we're going to calculate is in milliliters. As I said, we're going to use numerical integration for obtaining the volume variation. And then here we have again another scaling. As I said, in our codes, we are going to use in meters. Our STL file are now in meters. So here we make the volume in meters also, because we have it in milliliters, as I mentioned just now. And then as I said in the slides, we also know the equation of the volume with the short and long semi-axes. So we're going to calculate the volume, the temporal evolution of these semi-axes using the volume we have just calculated. And well, if we run this, we will also get the volume image that you see there, where our minimum volume is 67 milliliters more or less, and the maximum is 145. And we have also calculated the temporal evolution of the semi-axes. And finally, as I said, as a fifth step, we are going to calculate the STL files by moving both the shell and the base plane points. As I mentioned on the slides, we're going to first calculate the scaling factor for the displacement of each point, and then here we're going to calculate both the shell and the base moving points, and then write each STL file for each time instant. So if we also run this section, we will see that we have gotten the 100 STL files as we have declared before. And finally, also, if we want to extract the inlet and outlet data for our volume variation chart, you may also extract it here. In our case, we're using the flow rate and calculating the velocity with the inlet tube we have, and also the flow rate for the outlet data. And then we will going to save it as CSV files. And you can see here in the picture how we get this inlet velocity, which in the systole is closed, and then the outlet outflow, which is closed in the diastole and then open in the systole. And well, this is the methodology we have used for the obtention of the STL files for an idealized geometry. So well, now that we have created the STL file evolution with our MATLAB script for the idealized left ventricle model, we want to go to the second part of this video, which would be applying the same methodology but for a patient-specific geometry. But before we go to the MATLAB script of this patient-specific geometry, we are going to show you also how to do the segmentation and the pre-processing of the cleaning and the cutting of these left ventricle surfaces, and so that you can take your medical data and obtain these patient-specific geometries. So for that, we're going to go back to our PowerPoint. You can see here the scheme of how we're going to do this. First, we're going to use the 3D slicer to do the segmentation from our cardiotomography scans. I also leave you here the video of how to do the whole heart segmentation. In our case, we're just going to do segment the left ventricle, the aorta, and the left atrium. Then we're going to pre-process this to cut the unnecessary parts of the left ventricle and redimension it, close the holes and all, and get this kind of starting geometry. So for that, as I said, first we need to do the segmentation on 3D Slicer, and I will leave here on the slides this kind of step-by-step tutorial, but and I will go doing it on my own on the app after I mentioned 3 kind of general ideas. So well, after we load the data in 3D Slicer, we are going to crop the volume so we get some kind of isotropic volume space and spacing for all of the slides that we have in our CAD tomographies. Then we're going to use the segment editor to kind of create the seeds and grow from them to create this kind of a closed surface of our left ventricle and take away all of the other cavities present in our heart. And finally, we're going to have to also fill some holes or do some smoothing to create some kind of a smooth surface that we need for our simulations. Because also, of course, the clinical data it has some discrepancies, so you don't generate this kind of fine and smooth geometries. And finally, we're going to export this data as STL files. So if we go now to Slicer, so as I said, first thing we want to do is to add our data. For that, we're going to use File, Add Data, and choose our file that we want to add here. In my case, I will add this, and you can see here, once we have added these volumes, we get this kind of 3 views of the heart. And now we need to crop the volume, and for that we're going to go to filters, and here we're going to select converters, crop volume, and this way, after applying fix, we're going to check the isotropic spacing, and here we're going to put the spacing 3 times, and we can apply, and now we will have all of the slides in the same cropped volume. We can check off this display ROI, and then we will have, as I said, our cropped volume. So now in modules, we want to do the second step, which would be the segmentation. We will take the segment editor tool, and here we are going to add the left ventricle, left ventricle here. But also we're going to add another index for the others, which will be other tissues, other cavities that we don't want to take into account when we grow our surfaces from the seeds. And so once we have this declared, we're going to paint, which you can change here your brush diameter. And well, what you want to check first is this view. Here, this thing is the left ventricle. So if we scroll, we will get also the aorta. So we're going to put the seeds here, the left ventricle, and also in the aorta. So we get also the outlet of this left ventricle. And as I said, then we want to take out all of these tissues, other cavities such as the right atrium, and all of this. So then if we scroll a little bit more, we will get the left atrium, which is the inlet for our left ventricle. And again, all of these other things, we don't want them. So this will be sufficient, but we can also go to other views. For example, here, this is our left atrium. This is your left ventricle. So we also want to put there our seeds. This is the aorta. And again, if we take all of this out, better, because then the seeds will grow better and the surfaces will be better defined. And we can do the same here. We have our left atrium, the left ventricle, the aorta, and again, we will take all of the rest out. Here too. So well, you can continue slide by slide defining, but it's sufficient to put just some seeds on our pictures. And now we're going to go here to the Grow from Seeds tool. We will initialize it so it computes the differentiation between the left ventricle, the aorta and left atrium, which we have painted in green, and the others, which will be yellow. So as you have seen, it has differentiated it, and now we're going to click apply. And once it's applied, we are going to go to this green arrow, which says go to segmentation model. And finally, we're going to create a closed surface. So here we go to the 3D view, center the view. We're going to see this kind of our left ventricle with our aorta and the left atrium here. So as you can see, we have this, but it's not really smooth. If we go to a CFD solver with this, this is not really a really smooth surface. So what we are going to do here is go again to the segmentation tool, segment editor tool, and we can do two things to smooth this up. We can check here in editing 3D views, click in ventricle, and we can go to these things where we can see that there are maybe big holes and fill it. So we can get a smoother planes, but take care because you can alter the geometry and we don't want to get that. Another thing we can do is to use another tool here that is called smoothing. We are going to set the smoothing method to joint smoothing, and here we can add the smoothing factor, so we get a really smooth geometry, and apply. And as you can see, now we have a little bit a better geometry, even though we have some holes that this will penalize our simulation. So we have to go to paint again and fill those holes, but without altering our geometry. This is also only to help our smoothing tool that we have just used. So we don't want to create anything more than what's already defined, but just give some help here. If you double click, this maximizes to see it better. And then, as I said, we can again apply our smoothing to get something of a more closed geometry. Again, if we have this kind of ugly holes, we can paint a little bit over it. But well, we have some kind of a good smooth closed surface. I don't want to go away. Well, okay, there you go. And we have this, which now we can export as a STL file and apply the following cleaning and repairing tools. So for that, we're going to go again to modules, data, right click on left ventricle and export visible segments to models. And once we have created these models, we can again right click the left ventricle, export to file, and after choosing your name and the directory you want to save, you have to also export as an STL format, and we can click export and we will get our STL file generated. So once we have created this STL file on 3D Slicer, we want to, as this file still or surface is still not good defined, we're going to use MeshLab to clean and repair this geometry. We're going to cut also the left atrium and aorta, which we only want to use it as, in our case, as inlets for the left ventricle. And afterwards, we are also going to apply in ParaView. We're going to also use ParaView to apply some scaling, some rotation, and some translation, so we orient and have our left ventricle well positioned. So now, as I said, we're going to go to MeshLab, and we're going to apply the repairing and the closing of the removing of the unnecessary parts. So for that, we're going to file import mesh, select our left ventricle STL file, okay. And here, as you can see, we have now loaded our mesh, our surface mesh. So here it is important now to first use a filter of removing the isolated pieces. So for that, filters, cleaning and repairing, remove isolated pieces with the diameter. I always use 25, the percentage of the diameter, to catch all of the isolated pieces. We click apply, and you can see here that we have removed some vertices. So there were some kind of vertices outside our main surface. And now in edit, we are going to select faces in a rectangular region. And once we have oriented this well in our 3D view, so it's aligned with the aorta, we are going to use this tool to select the faces that we want to remove from the aorta. And afterwards, in filter selection, we can delete selected faces. So you can see now that in the aorta we have some kind of a plane for our outlet, and we have to do the same for the inlet. We have to remove this kind of left atrium. You can also use ParaView and Clip or other softwares to do this kind of clipping. This is the fastest way that I can show you. And again, we're going to select faces. Of course, I'm doing it fast, and it's not maybe the best outcome, but you can do it more slowly and remove this a little bit more correctly. And well, now we have this kind of inlet and outlet in our left ventricle. And the next step would be to close those holes. So for that, we're going to use filters, remeshing, simplification, and reconstruction. And we have a tool called close holes. Here, it is important for you to edit the max size, so you catch all of the hole. I put it in 1000, for example, and we apply once or more, so everything is closed, until we see here that even though there are holes, no new faces were created. You can see here that we still have this, even though this has closed, we still have that hole there. So now we're going to apply another filter, which is in remeshing, simplification, and reconstruction. It's called remeshing, isotropic explicit remeshing. Of course, you have all of these steps on the slides on the PowerPoint, so you can follow it better there. And here we're going to apply this. So you have seen that we create a more isotropic mesh on the surface, and we are going to again apply the close holes with this geometry, and you can see that now we have closed the hole and there were 0 holes detected, so 0 new faces. So now we have closed this kind of holes that we have generated when removing the aorta. We can again, if we want, apply the remeshing to kind of have a good isotropic mesh. And now once we have this, we are going to export it. So for that, we will choose File, the tab, and Export Mesh As. And here we will choose the name, and we will save it wherever we want with the name we want. For example, we will call it left ventricle clean. So we know that this is the clean version and without the aorta and the left atrium. So as I said, the next step would be to take this and go to ParaView, because you will see now that if we upload our mesh into ParaView, and if we check the axis grid, you will see that the dimensions of it, well, apart it is not aligned with any axis. Our ventricle also, the size, it's too big for a heart. It's 120 units, and we want to have, if we think in meters, one left ventricle would be more or less 10 centimeters, so 0.1 meters. So we're going to use here the filter transform, alphabetical filters, alphabetical and transform. You can also search on filters and put transform. And here we first we want to scale it down to meters. So it's more or less the height of the ventricle is apply, and then we can center again, and you can see here that now the ventricle is more or less 10 centimeters. You can also leave it in without the scaling, then you will have to define afterwards that you are working in millimeters or whatever scale. But in our case, we're going to work with meters. So we have that. And then you also have to play, so you align this left ventricle with the set axis. In our case, we want to align this with the set axis, and we want to have the zeta 0 plane, the x 0 plane here, the zeta 0 plane here. So you can play with this by rotating it, translating it here using these values for translation. And I also recommend you to use the sources alphabetical plane. You can define 3 planes, which would be this would be the XY plane, the XZ and the YZ, and then you can kind of get a better view of how you are rotating and translating your ventricle. So as you can see, I've done all of this work or iterating, and as I said, defining this kind of 3 planes, that so I can see where it's located. This would be the X0 plane, so I have this ventricle center there, also in the Y0 plane, and the most important thing is that it's scaled correctly, and the zeta 0 plane is more or less under the, well, the ventricle is aligned with the Z axis, and the zeta 0 plane is more or less a little bit below the inlet and outlet of the ventricle. So in the afterwards in the script we can define that we want to how we want to display the points from here down, because of course we don't want to move the points here in the inlet and the outlet. And then you can see how we have gotten this ventricle. So finally we have to here click on the transformed ventricle, and we will file save data, and again we are going to export the STL file by, for example, patient specific point STL name, and we will extract this STL file. So going back to the slides, we have already done this kind of segmentation, cleaning and scaling, and now going back to the MATLAB script that we have earlier defined in the idealized model. In this case, for our left ventricle, the script will be really similar, but in our point classification, we are going to define that the inlet and outlet area up until Z0 is not moving, and then the displacement will grow when we approach the apex. But again, the methodology is the same. We extract the volume variation by integrating the flow rate data, and define each time step of the ventricle using this volume variation. The thing is that here, as I said, the displacement will change from when we are near the apex. We will have more displacement. We'll use an iterative algorithm to fit the volume, and the displacement here, as we don't know, it's not as in the ideal case where we have a semi-ellipsoid and we know how the axis is moved with the volume equation. Here we're going to displace the volume from the normal when we grow to the outside and when we are reducing the volume to the inside. So now checking out again the pseudocode graph, we have this kind of changes. In the load geometry, we have to also compute the initial volume and the phase normals, since it's not something that we have calculated. And also, in the generation of the STL files, as I said, it's going to be an iterative method of adjusting the vertex displacements to match the target volume, which is the one that we have on the graph, with the current volume we have created when applying the displacement. So it will be an iterative optimization loop. So now going back to MATLAB, we will we'll go to the script that we will provide of the generation of the STL files in patient-specific geometries. And again, we will clean our workbench. And as you will see, all of these, all of the things that have not changed will be really similar. So here we have the loading of the initial mesh, the scaling, which in this case, as we have scaled it to in meters in ParaView, we don't have to do any scaling, so the scaling will be 1. But in case you are having it in millimeters or whatever, here you have the scaling. So because again our code is in meters, then here we will compute the initial volume, which as in this case is not a geometry we know. We will need to compute it with this function. And finally, also apart from extracting the points and the connectivity, we want to compute the phase normals of this initial mesh. Also, we identify here the minimum point of in the vertical axis, so we can use it afterwards on the creation of the STL files. So if we run this, we will get the following figure. As you can see, we have loaded our mesh. Again, in this part, we're going to classify the moving points and the static points. As we have done the pre-processing in ParaView and defined the Z0 plane as the moving, as the frontier of the moving and the static points, it's quite easier here. So if we run this, we will see how we obtain this graph, which we have seen in the slides, and we have more displacement the more that we get close to the apex. Then the computation of the flow rate chart, its interpolation, and the calculation of the volume variation, it's similar to the one in ideal. In this case, we are not computing the semi-axis because we don't have these things. So we will load our flow rate data, and we will also compute the volume variation. And finally, the major change in this script is the loop of generation of the STL files, where basically what we are doing here is an optimization loop where we are defining the displacement of the points, trying to match the target volume we are taking from the volume variation graph here, and the total volume, which is the volume we calculate from the displacements. So even though this is not the most realistic movement of a patient-specific heart, this is a proof of concept that we want to do to try to do a next step towards from the idealized case to a more patient-specific case. And finally, after creating here the STL files, which takes a little bit more time than before because of this optimization loop, we can also compute again the inlet and outlet boundary conditions that come from the flow rate data. But again, this script is very similar to the one that we have seen before, with the difference of having this optimization loop on the STL generation. So going back to our slides, we can see now the results that we have extracted from these scripts and all of this methodology. We can see both the ideal heart and the patient-specific heart, how the volume change in time. And then we have created in our STL directory, we have all of these STL files that define the evolution of the wall, which we can later on introduce it in our simulations. So well, that was all for today. If you have any questions, you can look us up on our website that you have this QR code, and also you will have it in the link in the description of this video. And it was a pleasure to give this tutorial to all of you, and I hope that it was clear, easy to follow. And if you have any problems, as I just said, any questions, problems, we will be really glad to hear from you and to have your feedback. Thank you all.